Hello everyone, I am Faranju from Sri Venkateshwara College of Engineering, Bangalore. The topic for the presentation is Analysis of Algorithms from the course Design and Analysis of Algorithms. The contents of this presentation are: what is an algorithm, characteristics or properties of an algorithm, algorithm design and analysis process, why is algorithm analysis important, analysis framework, types of algorithm analysis, time and space complexity, asymptotic notation analysis, example for an algorithm, selection sort, advantages of design and analysis of algorithm. First, we will see what is an algorithm. An algorithm is a set of commands that must be followed for a computer to perform calculations or other problem solving operations. An algorithm is a finite set of instructions carried out in a specific order to perform a particular task. It is not the entire program or code, it is a simple logic to a problem represented as an informal description in the form of a flowchart or pseudocode. Characteristics or properties of an algorithm. Input. Zero or more quantities are externally supplied as input. Output. At least one quantity is produced as an output. Definiteness. Each instruction is clear and unambiguous. It must be clear what should be done. Finiteness. If we trace out the instruction of an algorithm, then for all the cases the algorithm terminates after a finite number of steps. Effectiveness. Every instruction must be very basic so that it can be carried out in principle by a person using only pencil and paper. It must also be feasible. Algorithm design and analysis process. First, we need to understand the problem. Then, we need to decide on the computational means, exact versus approximate solving algorithm design technique. Then, we need to design the algorithm and then prove the correctness of the algorithm designed, analyze the algorithm, and then at last code the algorithm. Now we will see why is algorithm analysis important. What is an algorithm analysis? Algorithm analysis refers to how to investigate the effectiveness of the algorithm in terms of time and space complexity. The fundamental purpose of algorithm evaluation is to decide how much time and space an algorithm needs to solve the problem as a feature of the scale of the input. Importance of algorithm analysis. To forecast the behavior of an algorithm without putting it into action on a specific computer. It is far more convenient to have basic metrics for an algorithm's efficiency than to develop the algorithm and access its efficiency each time in a specific parameter in the underlying computer system changes. It is hard to predict an algorithm's exact behavior. There are far too many variables to consider. As a result, the analysis is simply an approximation. It is not perfect. More significantly, by comparing several algorithms, we can identify which one is ideal for our needs. Analysis framework. Both time and space efficiencies are measured as functions of the algorithm's input size. Time efficiency is measured by counting the number of times the algorithm's basic operation is executed. Space efficiency is measured by counting the number of extra memory units consumed by the algorithm. The efficiency of some algorithms may differ significantly for inputs of the same size. For such algorithms, we need to distinguish between the worst case, average case, and best case efficiencies. The framework's primary interest lies in the order of growth of the algorithm's running time as its input size goes to infinity. Types of algorithm analysis: we have time complexity evaluation, space complexity evaluation, worst case, best case, and average case evaluation, asymptotic notation analysis. First, we will see time and space complexity. Time complexity. Time complexity is a type of computational complexity that describes the time required to execute an algorithm. The time complexity of an algorithm is the amount of time it takes for each statement to complete. As a result, it is highly dependent on the size of the processed data. It also aids in defining an algorithm's effectiveness and evaluating its performance. Space complexity. When an algorithm is run on a computer, it requires a certain amount of memory space. The amount of memory used by a program to execute it is represented by its space complexity. Because a program requires memory to store input data and temporal values while running, the space complexity is auxiliary and input space. Asymptotic notation analysis. The asymptotic notation analysis are used to calculate the running time complexity of an algorithm. Usually, the time required by an algorithm falls under the three types: best case, average case, and the worst case. Best case, minimum time required for program execution. Average case, average time required for program execution. Worst case, maximum time required for program execution. Big O notation is denoted by O. The notation O of n is the formal way to express the upper bound of an algorithm's running time. It measures the worst case time complexity, or the longest amount of time an algorithm can possibly take to complete. For example, from the alongside graph for a function f of n, O f of n is equal to g of n, there exists c greater than 0 and n naught, such that g of n is less than or equal to c into f of n for all n greater than n naught. Big omega notation is denoted by omega. The notation omega of n is the formal way to express the lower bound of an algorithm's running time. It measures the best case time complexity, or the best amount of time an algorithm can possibly take to complete. For example, from the alongside graph for a function f of n, omega f of n is greater than or equal to g of n. There exists c greater than 0 and n naught, such that g of n is less than or equal to c into f of n for all n is greater than n naught. Theta notation. It is denoted by theta. The notation theta of n is the formal way to express both the lower bound and the upper bound of an algorithm's running time. Some may confuse the theta notation as the average case time complexity. While big theta notation could be almost accurately used to describe the average case, other notations could be used as well. For example, from the alongside graph for a function f of n and g of n, theta of f of n is equal to g of n if and only if g of n is equal to O of f of n and g of n is equal to omega of f of n for all n greater than n naught. Now we will see an example. Algorithm for selection sort. We need to set the minimum for the first location. Search the minimum element in the array. Then swap the first location with the minimum values in the array. Then we need to assign the second element as minimum until we sort the entire list of array. Selection sort. This algorithm repeatedly selects the smallest element from the unsorted portion of the list and swaps it with the first element of the unsorted part. This process is repeated until the entire list is sorted. Here we have been given the unsorted list. Passes are nothing but the number of steps we need to perform to sort the unsorted list of array. Number of passes is equal to n minus 1, where n is equal to the number of inputs. First, we need to search the minimum element from the unsorted list. Here in this example, 5 is the minimum element. We need to swap the position of 5 with the first location, that is 64. Then we need to select the second minimum element, which is 7. We need to swap the second position with 7. We need to perform this until we get the sorted list. Then we will see the advantages of design and analysis of algorithm. Improved efficiency. A properly designed algorithm can notably improve the performance of an algorithm, leading to quicker execution instances and reduced resource utilization. Better scalability. As the size of the input information will increase, poorly designed algorithms can quickly turn out to be unmanageable, leading to slow execution times and crashes. Improved code exceptional. A nicely designed algorithm can result in better code first rate standard because it encourages developers to think seriously about their application's shape and organization. Increased innovation. By knowing how algorithms work and how they can be optimized, developers can create new and progressive solutions to complex problems. Competitive benefit. In industries where pace and performance are vital, having properly designed algorithms can provide an extensive competitive advantage. Thank you for watching the video.